In this video, we're going to continue our study of some basic properties of Laplace transforms. In the previous video, we looked at the definition of Laplace transforms and we looked at a couple of applications. We learned that the Laplace transform of e to the at is 1 over s minus a, and we learned the Laplace transform of 1 is 1 over s. The first thing we're going to do here is look at something called the linearity property, which is very important, something we'll be using a lot in this chapter. I'm going to try to make the connection with differential equations as soon as I can, but we need a few basic facts about Laplace transforms before we're going to be able to do that, and this linearity property of Laplace transforms is one of them. So that's the linearity property. Here's another way to write it in our short table of Laplace transform facts. So again, I'll be handing out a much longer table to my students in class near the beginning of this chapter. But once we have our linearity property, we'll at least know those four things, and that will be almost everything that we'll need for the connection with differential equations, at least for starters. We're going to go ahead and look at the proof of the linearity property here. And just like all the other examples that we've looked at so far, all we need to do is take our function, whatever we're trying to find the Laplace transform of, and plug it into the definition of Laplace transform. So that's what's happening here. I'll usually ask students to do something like this in the homework and sometimes on a quiz or test as well. Usually I'll give them some other transform like a Fourier transform, Fourier sine transform, or Fourier cosine transform to try the derivation of the linearity for those things is very similar to what we're going through here. So in the first step, I just took the function alpha f plus beta g and plugged into the definition. The next step, I just broke that up, multiply out the e to the minus st in both terms, and then break up the integral into two integrals. And in the first integral, we have alpha, which we're thinking of as being a constant, which we can pull out from the integral. That's what's happening here. And similarly, in the second integral, we have beta, which we're thinking of beta as being a constant, and we can pull that out from the second integral. Once we do that, once we pull out alpha from the first integral, all that's left is just the definition, the original definition. So that's the rest of that is just the Laplace transform of f of t. And if we examine this and compare that to the definition of Laplace transforms, we see that must be g of s, the Laplace transform of little g of t. So that proves the linearity property, property number 4 in my short table. Here's a quick illustration of how we use the linearity property. Another way to think about the linearity property is we just take Laplace transforms term by term. Just like the student by now has had a lot of experience calculating derivatives term by term and integrating term by term, and in a similar way, when we're calculating Laplace transforms, we can calculate Laplace transforms term by term, and that's what the linearity property does for us. So here's a simple example. Suppose we wanted the Laplace transform of the function 6 minus 4 e to the minus t. From the linearity property, the Laplace transform of a difference must be the difference of the Laplace transforms. Then we can pull out 6 from the first part. So that would be alpha in terms of my general formula, a constant that we can pull out. We can pull out 4 from the second part, and then we just have the Laplace transform of 1, which is 1 over s, and the Laplace transform of e to the minus 2t, which is 1 over s plus 2. So using linearity, we immediately get that function of s for the Laplace transform of 6 minus 4 e to the minus 2t. We will be doing various algebraic manipulations with Laplace transforms soon enough, but for now we'll just leave the answer in that form. You could find a common denominator there, but we don't really need to worry about that right now. Example 4 is maybe a little more interesting application. We can actually use the linearity property to calculate the Laplace transform of hyperbolic sine. There are some exercises in my book which involve doing this kind of thing as what I think is a nice shortcut method for calculating the Laplace transform of hyperbolic sine, hyperbolic cosine, and sine or cosine, using Euler's formula and things like that. Of course, those things can all be calculated by using the definition and doing some integration, but I think these shortcuts are probably easier to work through the calculations. So the first thing I did here was I just plugged in the definition of hyperbolic sine, which hopefully the student has seen before. Then I used linearity to pull out the 2, and that just leaves the Laplace transform of e to the at minus Laplace transform of e to the minus at. And from formula number 2 in my table here, I know that the Laplace transform of e to the at is 1 over s minus a, and the Laplace transform of e to the minus at must be 1 over s plus a by plugging in negative a in place of a in formula number 2. And now I'm going to go ahead to get this into the form that we want. I'm going to go ahead and find a common denominator here, which is s minus a times s plus a. And fixing up the numerators, we have s plus a minus the quantity s minus a, which simplifies to just 2a. So that gives us that expression for the Laplace transform of hyperbolic sine, 1/2 times 2a over s squared minus a squared, where we now have multiplied out in the denominator, and then canceling the 2's, we get a over s squared minus a squared, which is one of the basic formulas in my Laplace transform table that I pass out in class. For the application to differential equations, we need one more very important piece, which is called the operational property, a connection between the Laplace transform of a function and the Laplace transform of the derivative of the function. We're going to go ahead and look at the proof of that. Just like all the other proofs we've looked at, the first step is to just take whatever we're working with and plug it into the definition. That's what's happening there. Just replacing f of t in the definition of Laplace transforms by f prime of t. And now the idea is to use integration by parts. We'll let u be e to the minus st, and dv is f prime of t dt. Hopefully integration by parts is a technique of integration which the student has seen somewhere before in Calculus 2 or something like that. The student may need to review that to follow this example. Integration by parts is basically just the integration version of the product rule for derivatives. If we let u be e to the minus st, then differentiating that, du will be minus s e to the minus st dt. And over here, if dv is f prime of t dt, we go the other way. We integrate or anti-differentiate that to get v, so v would just be f of t. So those are the ingredients for integration by parts. This is just the standard integration by parts formula for a definite integral, and we're being a little bit informal with the way we're treating the limit here, which is similar to some things we did in an earlier video, kind of handling it the way an engineer or physicist might do if they weren't too concerned about the niceties of the mathematical theory. So just plugging everything in, plugging in u, v, and v du, we get that expression. And notice in the second part, when we plugged in v and du, I pulled out s. Actually, I pulled out minus s, so that gave me a minus, so it turns into a plus. Then I pulled out s, which is constant from the integration there. And notice that integral in that term is just the Laplace transform of f. So that gives us s, big F of s there. And all we need to do now is think about the rest of it, the integrated part. So again, being a little bit informal with the way we're writing this, there's really a limiting process going on here. If s is something positive, and if our function f is well behaved, at least if it doesn't grow any faster than whatever s is, then this dying exponential is going to overwhelm our function f, and that term will end up just dropping out. That term which you get from the upper limit. From the lower limit, when we plug in t equals 0, we just get that. So we're ending up with s, big F of s minus f of 0, as was claimed up here for the Laplace transform of the derivative. And now that we have all the ingredients that we need, we can look at an application to differential equations. That's what's happening here in example 5. We have a first order constant coefficient dE with initial condition y of 0 equals 4. I generally ask students to try this problem using one of the other methods that we learned earlier in the course. The differential equation is first order linear. It's also separable. I'm not going to go through those details in this video, but hopefully the student knows how to use one of those methods to calculate 10 e to the t minus 6 for the solution of that initial value problem. Now we're going to go ahead and see what a Laplace transform approach to that problem looks like. The first step with a Laplace transform approach is to take the Laplace transform on both sides of the differential equation. Next, we use linearity on the left-hand side. The Laplace transform of a difference is the difference of Laplace transforms. And we know the Laplace transform of 6 is 6 over s, so we plug that in there. So we'll pick it up right there in the next video in the Laplace transform solution of this differential equation. Hopefully, again, as a friendly reminder, hopefully the student's taking at least a few notes as they're working through these videos. So we'll pick it up there in the next video.